We read about the postulate of quantum mechanics. In the fifth postulate, we saw that it talked about time evolution of the state, right? The first postulate was all about defining the state. The other three postulate was about determining the state at t equal to 0, that was talking about statics. And the fifth postulate was about dynamics, means how to find how the state of a quantum system changes with time. According to the fifth postulate, the Schrodinger wave equation was d psi is a function of position and time. So d psi by dou psi by dt equals to h psi. So the Hamiltonian consisted of the potential energy, or I'll write Hamiltonian was equal to Ke operator plus potential energy operator, right? And kinetic energy is, if I talk about non-relativistic domain, it is P square by 2m plus V, and the operator corresponding to P was equal to h cross by I d psi by dx, or in 3 dimension it is h cross by I into gradient of psi, right? Gradient of psi. So kinetic energy operator is going to be the potential, the momentum square, so it will be minus h square upon 2m del square psi. So this is going to be minus h square by 2m del square. If I don't put I don't have to put psi, in fact this is p psi. I'm very sorry, the operator we won't put this over here to remain an operator only. Okay, so this is plus V operator. So if I put everything over here, it will be IH cross d psi by dt equals to minus h squared 2m plus V psi. This is going to be the Schrodinger wave equation. So in general, I write IH cross d psi is a function of position and time, h square by 2m del square plus V can be a function of r and time, and psi can be a function of r and t. Right? This is, you can say, time dependent. This is complete time dependent Schrodinger wave equation. Right now I'll confine myself to the potentials which are not time varying. Right now I'll confine to those problems where the potential energy does not depend on time, where potential energy does not change with time. So if we assume if the potential energy or the potential does not change with time, if the potential energy does not change with time, in that case your VRT is basically VR, right? So in that case, this Schrodinger wave equation is going to be equals to minus h square by 2m VR psi RT. Now we can apply separation of variable. I can apply separation of variable and I can write psi RT as, say, phi R and FT. Phi R and FT. So if I put it over here, I'll be getting IH cross. So this will become FT, and since, oh sorry, it will become phi will come outside, and this become df by dt, because f is a function of time only. And this side it will be h square by 2m ft del square phi r, and vr phi r ft. So if I divide the whole equation by phi r into ft, this will be IH cross 1 by f df by dt minus h square by 2m, and this will be what? 1 by phi r del square phi r plus VR. So you see, the left hand side is a function of time and right hand side is a function of space. Left hand side is a function of time, right hand side is a function of space. So they are equal. When they are equal, they must be equal to a constant. So the constant is E. E is the constant. So this method is called method of separation of variable, right? So I'll get two equations from here. One will be h square by 2m 1 by phi del square phi plus v equals to E, and the other equation will be IH cross 1 by f df by dt equals to E. So if I rewrite the equation, this equation is nothing but del square phi minus 2m by h cross v phi equals to minus 2me by h cross square into phi. So the equation will finally turn up to be del square phi plus 2m by h square e minus v phi equal to 0. And what is this? This is time independent Schrodinger wave equation. Time independent Schrodinger wave equation. And this equation will be how much? This will be df by dt equals to minus IE by h cross f, right? So if I solve this, this will be simply ft equal to some constant into minus it by h cross, right? Fine. So I'll solve this one, and from here, for the given problem which is characterized by the potential, any problem, quantum mechanics, any system will be characterized by the potential energy. Potential energy tells you about the interaction taking place in the system. Potential energy characterizes the interaction taking place in the system. So one of the particular solution will be, one of the solution of this equation, see, you got two equation. This is del square phi r plus 2mh square e minus vr phi r equal to 0. So from here you get the space part of the function. This I basically wrote psi rt as this is the space part, this is a time dependent part of the function, and from here I get the second part of the function, that is, let's say ft equal to ce e to the power minus e t by h cross, right? So the solution, the one of the solution is going to be psi rt is going to be, this is one of the particular solution, this will be phi r into e to the power minus IET by h cross. I took the constant in the phi r itself. This particular solution is called a stationary state. This particular solution is called stationary state. Why is stationary state? Because the probability density psi star psi is stationary. It will be phi square phi, that is phi square, or say, you know, the probability density. This is the probability density. You find that the probability density, it does not change with time. It does not change with time. The probability density does not change with time. Get your point? That's why we call it stationary state. That's why we call it stationary state. Also, the spectrum of energy which you get for such a system is also not varying with time. The energy, the eigenvalues that you get, the value of E which you get, is also not changing with time. So this is called a stationary state. This is called stationary state. But remember, the general solution will be equal to what? General solution, if say the system is bounded one, then you will have the spectrum of energy values. This will be the allowed energy value. So you have many solutions, and the general solution is given by sigma Cn phi n r into e to the power minus ENT by h cross. If you have this, if you have the quantized, if the suppose the system is bounded one, if the system is bounded one, the spectrum of energy which is possible is discrete. You have discrete spectrum, right, of energy values, and corresponding to each eigenvalue you have eigenvectors, and the general solution will be superposition of all these solutions, or linear combination of all the solutions will give you the general solution. But remember, this is not a stationary state. This is not a stationary state. This is not a stationary state, because you see, if I write psi star psi, this is not independent of time. This is not going to be independent of time. So I mean to say, the superposition of stationary state is not necessarily a stationary state. Superposition of stationary state will not be in general a stationary state. Getting a point? So this is all about Schrodinger wave equation, and where do we use it? We use it to get how psi, we use to get psi RT basically. So we will see several examples where we will be using Schrodinger wave equation. Several problems we will take where we will be using Schrodinger wave equation to get the eigen function and the eigenvalues, to get the energy eigen function and the eigenvalues. It will give you the allowed energy values. It will give you the allowed wave function which you can use to describe the quantum system, and it requires the description of the potential energy of the system, because of course in case of Newton's second law, this was also dynamical equation of motion, so it required the full description of the forces acting on the system, whereas Schrodinger wave equation requires the full description of the potential energy. See, the force and potential, they are the two ways of describing the interaction taking place inside the system. They are just the two ways of describing the interaction among the particles, or interaction of the particle forming a system with the surrounding in a system, right? So Newton's second law make use of the forces. The Schrodinger wave equation make use of the potential energy. Once you know this potential energy, you will get the allowed values of E, and you will also